Hey guys, so in this video I'll be going through the solutions in a bit more detail of the networks revision test. So for this video I'll be going through the multiple choice section. Alright, so with this one there's typically questions like this, understanding what defines a tree. In this one, which edge should be removed from the graph below to make it a tree. So for this one you need to understand the definition of what a tree actually is, in that it cannot have any multiple edges or circuits. Here we can see two circuits, so A, B, and F make one, as well as F, D, and E. That tells me that two edges would need to be removed to make this a tree. So the answer for this one is E. It cannot be done by removing only one edge. If you look at the connection between A to B, if you get rid of that, we still have a cycle over on the right-hand side there. Question 2. The figure at right shows a road network connecting 7 towns. The distance between towns is shown along the edges. All right, so a bit of a shortest path problem. I mean, you could use Dijkstra's algorithm for this one, but that would probably take way too long. This one is much better done by inspection, so testing a few different ways. So I could go from A to B, down to F to G. That would make 41. I could try another one. I could go from A to C, because that's the shortest edge I can see, then down to F and down to G. That makes a total of 35. You go through, you try a few more, you'll find that 35 is the shortest path to get there. So that's our answer. So with those ones, a little bit of common sense. Always try and follow the shortest valued or lowest edges when you can. The maximum total flow from node A to node G. So node is just another word for vertex. All right, so this is a max flow min cut question. So a bit of trial and error again. Try a few different ones. This would be 48. This would be 33. I went through the middle, 36. I went through here, that's also 33. And that's our answer, 33. So with these ones, I usually do like the left and right. So cut off at the source, cut off at the sink, and then just do a few through the middle to test it. But again, common sense, don't go through heaps of edges. Don't go through the really high valued edges. Try and stick with the lower ones where possible. If the graph below was a connected planar graph, the number of vertices, edges, and faces is. All right, so first of all, let's start off with vertices. That's easy. We can see that there are 6. That already eliminates a few of these options for us. Number of net edges must be 9, because that's the only 2 options that are left. Now we just need the faces. It says if it was planar, so we would need to redraw this planar. So I'm going to just use a different color here. I'm going to redraw this edge here. So I'm just going to scribble it out. All right, so now we need to calculate the number of faces. We could use Euler's formula here to do it. That's completely fine. Or you could just do it visually. So that'd be 1, 2, 3, 4, and don't forget about 5. So 5 faces. A suitable Euler path for the planar graph below is. All right, so remember, an Euler path needs to cross every single edge. It can repeat vertices, that's fine, but it can only go to each edge once. And it starts and finishes at a different vertex. Now I'm just going to immediately get rid of option A, ABA. That definitely doesn't cross every single edge, so a little bit of common sense there. So with this one, remember for the conditions for an Euler path is it needs to have exactly 2 odd vertices or all even. And it's best to start at one of the odd vertices. So can't be E because that starts at an even vertex. Sorry, wrong one. Can't be D, sorry, starts at even vertex. All right, so if you look at option C, it goes from A to F to D to C to B to E. That definitely does not go across every edge. E to B to C to D to B to A to F to D. Again, doesn't go to every edge. So the answer must be B. So try and eliminate a few options where you can, and then just trial and error the remaining options. Four different tutors have different hourly prices in dollars. Four different subjects, which is shown on the table below. Amy wants to get tutoring on all four of these subjects. If she chooses to get each subject from a different tutor, which are the following allocations provide Amy with the minimum cost for getting tutoring in all four subjects? All right, so this one is a Hungarian algorithm question. So it is quite long. It will take quite a while. For this one, it's probably best to just look at my YouTube video on going through a Hungarian algorithm question. I can make a separate video for this one, but these questions do take quite a while. If you're ever really stripped for time and you don't think you will be able to finish a question in time, just try and use a bit of logic. Remember, you want to get the smallest possible values. For this one, it is going to be option E. You can also go through each 5 options and add up all the numbers. So June for further maths, Sharon for English, Sydney for Spech, Max for chemistry for the top one, get the total, and then go do that for the remaining 4 and see which one comes out to the lowest. Find the length of the maximum spanning tree for the following network. So normally we look at minimum, but this one is asking for maximum. Same thing as Prim's algorithm. What we do is we start with the highest valued edges, however, not the smallest. All right, so I'm going to start with 16. That's the highest valued edge. I am not going to incorporate the 15 because that's going to create a multiple edge, which then it won't be a tree anymore. I'm going to do the 14, the 13, and the largest value to that vertex in the middle is 8. So 14, 13, 8, and 16 gives a total of 51. The time in minutes taken for 4 technicians to complete 4 different types of repairs is shown in the table below. The tasks are allocated with 1 person allocated to each repair so as to minimize the time taken to complete the 4 different types of repairs. The total time taken in minutes. All right, so again, a allocation problem. Don't have to do the full Hungarian algorithm for this one. It's just an allocation. I'll start this one off. So start with a row reduction. Subtract the smallest value from every single row. Meaning the new values in here will be these. All right, so after that, we would need to do a column reduction. So looking at those new values, I would subtract 0, 0, 5, and 0. So all that changes is this column, 15, 5, 10, and 0. All right, so after that, I would need 4 lines to cover up all the zeros. So that's good. That's what we want. From this, if I draw a bipartite graph, So we had, who do we have? We had Jim, Lee, Stuart, that's right, ST, and Sam. Repair 1, 2, 3, and 4. Right, so Jim could do repair 1. Lee could do 1 and 4. Stuart could do just 2. And Sam could do 2 or 3. Okay, so from this, looking at my bar-par graph, Jim has to do 1, which took 20 minutes. That means that Lee has to do 4, which took him 10 minutes. Stuart has to do 2, which was 50. And Sam has to do 3, which was 35. So the total is 115. Okay. The table above lists the 10 activities in a project, the immediate predecessor, and the activity time. The latest start time for activity F is. All right, so activity F has a total of 1. If we look at all the prior to it, we can work this one out. Might be easiest if we draw this one. All right, so A and B. And coming off each of those, we have C and D. Now we have E come off C and D, so they're going to match up. C comes off A, and D comes off B. F also comes off of B, so I'm just going to go around. All right. Just in the interest of saving time, I'm not going to draw the houses, but I will draw the numbers. So 0, 5, 7. For this one over here, it's 13. For this, it'll be 16, 18, 22, 27, and then going back. Change color. 27, 22, 21, 16, 13, 7, and 9, 0. All right, so the latest start time for activity F. The time in front of it is 16. It has a time of 1. So 16 take 1. Therefore, the latest start time for F is 15. The project is modified and the following changes are made. Activity A is delayed by 5 weeks, activity F is delayed by 5, and activity G is delayed by 4. I'm just going to make those changes. I'm now going to have a brand new critical path here, so I'm going to pretty much do this again. Okay, so activity A will be delayed by 5, so that's going to become 10. F is delayed by 5, and G is delayed by 4. All right, so we go through, we recalculate. So 10, 7, 14, 17, 23, 24, 29, go back, 29, 24, 23, 17, 14, 10, 0, yep, that's fine, and 17, that'll be 11. All right, cool. So the critical path here is A, C, E, G, J, K. So the answer is E. All right, so with question 11, we have a bipartite graph. So this one is purely just about interpreting what it means. So which of the following statements is not supported by the graph? It's really just trial and error, so going through. So for example, the first one, all 5 students have equal number of VCE subject preferences. If you look at them, that's correct. That's true. All of them have 3 preferences, so each line to a subject represents a preference. English is the most popular subject. Yep, that's definitely true. It has, what is that, all 5, I think. Further maths is the second most, so that has 3, whereas this has 2, 2, 1, and 2. So yes, that's true. Math methods and psychology are equally preferred by students. Well, no, that's not true. Math methods has 2 and psychology has 1. On the directed graph above, the numbers on the edges give the maximum flow possible through each of those edges. The maximum flow possible through the network is 27, so the value of X is. All right, so a tricky question, this one. What we need to do is work out the cut that gives the max flow, so the min cut, and therefore figure out the value of X. So for example, we need that cut would obviously cut off the network, but it's probably not going to be the minimum cut because it is gone through quite a lot of edges. So again, a bit of a trial and error. For this one, it is that one. So the sum of those edges is 9 plus 10.5 plus 12. Hang on, sorry, we don't include the 12 because it's going in the opposite direction. Let me just rub that out. So this one is actually, 9 plus 10.5 plus whatever the value of X is, equaling 27. So therefore, X is equal to 7.5. So it is a tricky one, that one, because it can take a while to figure that out. But same rules when you're doing your max flow min cut stuff. Just try and go through the minimum number of edges, try and go through the smallest number. And just keep in mind, with the number 12 there, that's going back into the cut. Don't count it. All right, a few more to go. The network below shows 11 activities which are required to complete a project, together with the time it takes in days to complete each activity. The critical path for this project has a length of. All right, so we need to go through and we need to calculate the estimated completion time. So again, I'm not going to draw the houses just for the sake of saving time. I'll draw the numbers. It's 24. What's that one? So that'll be 24, the 8 and the 16. What's that? That's 18. This one will be 46. So the 24 plus 22, which leaves me on 58. So the answer is D. So with these ones, you kind of need to learn to sort of do it quickly, just to scribble the numbers on as you go through. All right, the above graph shows a number of one-way roads and the distance in kilometers along each road. Fred wants to travel from A to F along the shortest route. The number of kilometers that Fred will travel is, all right, so again, shortest path, trial and error. There's only really so many ways he can go. You could go 9, 14, and 10, which is 33. He could go 12, 12, and 12, which is 36. Or for this one, you could go the 9, the 12, the 9, the 10, and the 12, which is 31. So that is our shortest route. So it's trial and error. Again, common sense, try and stick to the lowest valued edges. A Hamiltonian cycle for the network above is. All right, so with these ones, remember, there can be more than one answer. It has to start and finish at the same vertex and has to visit every vertex exactly once. All right, so I'm going to straight away eliminate A because it starts and finishes at a different vertex. I'm going to eliminate B because it visits X twice. Could possibly be C. I'm going to eliminate D. It starts and finishes at different vertices. I'm also going to eliminate E because it doesn't have X in it. So just by trial and error or process of elimination, so that one has to be C. And you can test it. U, Y, X, Z, V, W, U. And lucky last, the activities and their completion time in minutes that are required to complete a project are shown in the network above. For this project, only one activity, activity P, can be crashed. The maximum time that activity P can be crashed before further crashing has no benefit is. All right, so for this one, bit of a process, we need to work out the critical path to start off with. So 0, 17, 13, this will be 25. This will be down here 20, 33. 35 and 41. So 41, 35, 22 down here, 25, 13, 19, and 0. All right. So the critical path here is a total of 41. So that's the earliest completion time. What we have here is P being a value of 12. We need to work out what that can be delayed by without delaying the project any further. Or sorry, not what it can be delayed by, but what it can be reduced by and still have benefits to the overall. All right, so the critical path there is a total of 41. Now, the nearest critical path beyond that one is 39. So that is obtained by going from the other direction, essentially 17, 6, 10, and 6. If you go that way, it has a total time of 39. Now, because the estimated completion time of the entire project was 41, and the next closest path is 39, it means that project P can be crashed for 2 minutes. Any more than that will not have any benefit, because the project must take 39 minutes anyway. So the answer is B. All right, so that's it for the multi-choice. Hope some of that helped a bit.